Hello, second video on planes and 3D using vector equations. My last video I showed you two forms of the equation that we could have for a plane, and in the next video, in this video rather, we're going to be looking at how to use that to find points of interception and nearest points. So here we go then. Let's say I've got a plane here. Here's my plane definition. 5x plus y minus z equals 1. And I've got a line L. That's a general line equation. So here's my point that I know, and here's my line vector, and I've got some multiple of it. So what do I need to find this point of interception here, P? Well, at the point P, both the point must satisfy both the plane equation and the line equation. And in effect, what we're doing is going along our line until we find the single value of t that satisfies both equations. So best way to do that is a bit of substitution. Here's my plane equation, and what I've actually got here in my line equation is three equations in one, haven't I? X, y, and z. So for my x value, I know that that is 2 plus 1 lot of t. So I could substitute that in place of the x value in the plane equation. There we go. So I'm going to put 2 plus t in there. My y value is going to be y plus 2 lots of t. So I can substitute that in place of y. There is 3 plus 2t. And finally, my z value is 4 minus 1 lot of t. So that's 4 minus t. And I can place that in place of z in the equation. So that lot, 5 lots of this, 1 lot of that, minus 1 lot of that equals 1 in my plane equation. Now if I collect up my terms, I end up with 8t. My sum of my units here, there's 9 of them there and 1 on the other side. Therefore that simplifies to 8t equals minus 8, and therefore t equals minus 1. So t equals minus 1 is the value of the parameter when the point on the line equation is also on the plane equation. So I can just substitute in the t equals minus 1 into my line equation with there's t equals minus 1, and if I calculate that out, I now have a point of intersection 1, 1, 5. So I've found therefore that this point here would be 1, 1, 5. Got to be a unique point, hasn't it? And a line and a point always intersect, except if the line is actually parallel with the plane in one of it. So effectively it is either our A1 or A2 vector down our line equation. Okay. Second thing what's useful to know is if I've got a point D here, so that's at 753, and I want to find how far away it is from my plane. Yeah, here's my plane here. So how am I going to do this? Well, actually, I'm going to use the fact that the normal curve, the normal side vector here, is going to give us our shortest distance from the point to the plane. If that wasn't true, I would be able to draw a triangle like this. Yeah, if that was the shortest distance, let's call it h for hypotenuse, because I'd have a right angle triangle here. But hang on, that can't be the shortest distance, because if this is a right angle triangle, I know this distance is definitely shorter. Yeah, going straight down my perpendicular line from the plane. And therefore that tells us that the shortest distance must be going straight down the normal vector. Now that's quite useful because that means I can now create a straight line, because I know the straight line goes through the point D and has a line vector using the normal. Yeah, there we are. So how can we use that with this plane here? Okay, so what we do know then is that a point on our line is going to be our D point. That's our 753, and we know that the line vector A must be the normal vector N, yeah, which we know from the plane equation is 3, 2, 1. And we can substitute that into the generalized equation and then do exactly what we did in the last part. We're now going to find the point at which that line intercepts the plane. So there's our line equation. R equals our start point, 753, and our normal, using that as the line vector. And we're going to substitute these values, our x, y, and z again, x, y, and z equations into our plane equation. So let's have a look at our plane equation. Here's our plane equation. So for x here, I can use 7 plus 3t. There we are, 7 plus 3t. And substitute that in place of x in our equation. For y, I've got 5 plus 2t. I can substitute that in place of y. And finally, z equals 3 plus 1t. I can substitute that in place of z here. Then I collect up my terms and I end up with 14t, and then I've got units here, 34 and 6 on the other constant on the other side. Therefore 14t equals minus 28 and t equals minus 2. Now if t equals minus 2, I can substitute that into my line equation. So there's my minus 2 for my t. I know what the two vectors are, so I calculate that out and I find that my closest point, my nearest point on the plane to the point is 1, 1, 1. So let's just go back to our diagram. We now know this point here is 1, 1, and 1. And if I know my 2 points now, 1, 1, 1 and 7, 5, 1, there we go. You make it down to here. If I know 2 points, excuse me, then using 3D Pythagoras, I can find the distance between them. Because the hypotenuse squared is going to be the difference of the x values squared, plus the difference of the y values squared, plus the difference of the z values squared. Yeah, we're just going across from one corner of a cuboid to the other corner of a cuboid. So we're going from this point here up to that point there. Yeah, and we're just using Pythag, 3D Pythag for that. So we've got d squared is going to be 6 squared plus 4 squared plus 2 squared. I believe that's 56, and therefore d is the square root of 56. And so by using the fact that we know the normal, that the shortest distance must be straight down the normal, yeah, from a point, must be straight down the normal, we can find our point, our nearest point on the plane, and we can find the distance between those 2 points using 3D Pythag. Yep, there we go. So in summary then of the 2 videos we've done, there are 2 ways of defining a plane. One's using the normal vector. Here's that form. So here we can see the normal vector very quickly is 4 minus 5 minus 1. That must be a constant. Let's collect, we can get that from any point we've got, or we'll just give it to us. Or we can use our 2 in-plane vectors. Our generalized point x, y, z is some point we know on the plane, plus some multiple of a vector a1 in the plane and a multiple of the vector a2 in the plane. And if we want to find the shortest distance from a point to a plane, then we can use the normal vector to find the shortest distance from the point to the plane. So we can create a line, we go straight down that line till we hit the plane, and that's relying on the fact that effectively the scalar product between the normal and any vector in the plane is going to be equal to 0. So there you go, that's the second video. Hope that's of use.